speaker, Sridhar Gopinath, is going to be talking about kilobyte-size machine learning models to tiny I/O devices. So one of the things we heard about yesterday in the Turing Award lecture was about these giant 100 million parameter models, and of course they take up a lot of space. And so we're going to hear today about models that are much smaller with high performance.
Hello. Hi guys, good morning. My name is Sridhar Gopinath. I am from Microsoft Research India. And today I'll be describing the SeeDot framework, which we have built to compile machine learning algorithms to very small IoT devices. With the advent of machine learning, we are now living in a world of smart devices. There are various applications in this space like smart healthcare, smart cities, smart homes, smart factories, and so on. But how do these applications really work? The current de facto approach is to deploy a large number of sensor or IoT devices to collect data. And the collected data is then transferred to the cloud where the smarts lie or machine learning algorithms lie. Machine learning algorithms are then run on this data and the results are sent back to the device. Although this approach works, but there are several number of applications where this is problematic. I'll explain a few of them. So FarmBeats and GesturePod are two applications built at Microsoft Research. FarmBeats is a data-driven application agriculture project where sensor devices are deployed in remote farms without internet connectivity. Here, researchers want to run machine learning algorithms to help farmers. But without internet connectivity, it is impossible to achieve this goal with ML in the cloud paradigm. GesturePod is another device which tries to improve accessibility. Here, the device attaches onto the white cane of a person with visual impairment, and machine learning algorithms are run to identify the gestures performed by this cane. However, if the machine learning algorithms are running on the cloud, it incurs network communication for each gesture. And that means that it incurs high energy consumption and significantly reduces the battery life of the device. Moreover, latency is a big concern these days, and users are not comfortable with sending their data, sensitive data like the history of gestures, to the cloud. So all of these problems have led us to explore a new paradigm where machine learning algorithms are not running on the cloud, but they're brought down to the devices and they're running locally on the device. This system is called as the intelligent device. Here, the sensor devices are no longer dumb data collecting devices, but are rather running machine learning algorithms locally on the device and then taking actions. However, implementing applications on top of this idea is still very hard because of the nature of these devices. The devices that we consider are very low-end microcontrollers and FPGAs, which have two major issues. The first one is that these devices have very low memory and compute resources. Second one is that these devices do not have any floating point unit. Fortunately, the first problem has been addressed by ML researchers, where they have developed new machine learning algorithms that can work with very kilobyte-size memory. These algorithms can now fit on these devices and can achieve very good classification accuracies. However, even these algorithms are expressed in floating point. But now, how would you take a floating point machine learning algorithm and implement it in a device which doesn't have any floating point unit? You manually can translate it to integer code. This is a very tedious task and no one wants to do it, and it incurs a lot of developer overhead. This is where SeeDot comes in. SeeDot is a framework which takes as input ML model or an ML inference algorithm. The SeeDot compiler generates integer programs which run efficiently on IoT devices. There are two main aspects of SeeDot, the language and the compiler. The SeeDot language can be used to express ML algorithms in very few lines of code. The SeeDot compiler automatically generates fixed point programs which doesn't have any floating point operations in them. In this talk, I'll focus only on the compiler. For more details about the language, please refer to the paper. To understand the challenges in building a fixed point compiler, let's look at the existing alternatives to SeeDot. In this graph, I compare the related work with x-axis mentioning the classification accuracy of the ML models and y-axis representing the performance on IoT devices. The first alternative is to perform floating point software emulation. Since the IoT devices do not have any floating point unit on them, the device manufacturers provide software libraries that emulate IEEE floating point standard using integers. This approach has zero developer overhead and provides high classification accuracies. However, emulations are very expensive and the performance on these devices become very low. Since floating point operations are very inefficient, another idea is to use fixed point representations which only contain integer operations. There are a variety of tools that do this. One of the popular tools like MATLAB, you use a concept of high-bitwidth fixed point to achieve this goal. They use 64 or 128-bit integers and try to achieve good classification accuracies. But MATLAB-like tools are designed for digital signal processing units which have hardware support for high-bitwidth fixed point. And on microcontrollers which lack hardware support for high-bitwidth fixed point, the performance again is really bad. To address this issue, one can think of using low-bitwidth fixed point representations which use 8 or 16-bit integers. That means that the performance on these devices is high, but as I'll show you later, the classification accuracies of these techniques is really bad. With SeeDot, we want to be on the top right corner. To improve performance, we want to use low bitwidth fixed point representations. And to improve classification accuracies, we have some nice techniques that I'll discuss. Before I talk about the SeeDot compilation process, I'll talk a little bit about the fixed point representation. A floating point number x can be represented in fixed point using two integers, y and k, where y is x multiplied by 2 power k rounded down to an integer. In this example, I'm using a 8-bit fixed point, which means that y is a 8-bit integer. K is also referred to as a scaling factor, and a higher value of k means a more number of significant bits for the integer y and implies better precision. To give an example, consider two variables pi and e with values 3.1415 and 2.7182 respectively. A good representation for the variable pi would be 100 with a scaling factor of 5. A lower scaling factor means lesser precision, and a higher scaling factor would mean overflows. Similarly, the variable e could be represented as 86 with a scaling factor of 5. Arithmetic on fixed point numbers also suffer from overflows. To give an example, adding pi and e with a scaling factor of 5 overflows and produces minus 70, which is garbage. So one needs to follow certain standard fixed point arithmetic rules to generate to make sure that there are no overflows. I'll explain these rules with an example. Consider two floating point numbers a and b represented as x comma k and y comma k respectively. For 8-bit fixed point addition, the result can be a 9-bit integer. To guard against overflows, the scale of the operands are reduced by 1 by right shifting the numbers by 1 bit. By doing so, now you can add these two numbers by guaranteeing that there will be no overflows. Simultaneously, the scale of the result will be 1 less than the scale of the operands. Okay. Similarly, for fixed point multiplication, the result can be as big as a 16-bit number. Again, to make sure that there are no overflows, the operands are scaled down by 4. Now the product can fit into an 8-bit integer. The scale of the result is then adjusted accordingly. The rules are similar for subtraction and division, and I have skipped it for now. As you can see, the scale values for the result of each arithmetic operation is smaller than the original scale values. While it is necessary to perform scale down operations to make sure that there are no overflows, each scale down operation takes down one significant bit. which means that by doing each scale down operation, you're losing precision. And you have to make sure that you don't do a lot of scale down operations. So with these rules, now can we convert a floating point program to a fixed point program? This is what I'll show next. There is, on the left is a ML algorithm which contains floating point variables, and on the right is the fixed point code generated using the rules I described in the last slide. As you can see, the variables at each point in the program, there are a lot of scale down operations. The variables lose significant bit at each part of the program. And towards the end of the program, the variables lose all significant bits and the results will be garbage. To make this case concrete, we actually implemented this approach on our benchmarks and found that the resultant classifier is equivalent to a random classifier which generates, which is very imprecise. So this is a problem that we are trying to solve. How do we improve precision of fixed point programs? To do so, we are using two insights. I'll talk about them one after the other. The first insight is that in the fixed point programs, you can avoid the scale down operations towards the end of the program. To explain this, assume a boundary that is dividing the fixed point program into two parts, the prefix part and the suffix part. In the prefix part of the program, standard fixed point arithmetic is performed and the scale down operations are used to make sure that the variables do not overflow. And because you are conservatively performing a lot of scale down operations, the values of these variables will become really small towards the boundary. In the suffix part of the program, you conservatively assume that the variables do not overflow and do not perform any scale down operations. By doing so, you are retaining a lot of significant bits in the suffix part of the program. And this improves the overall precision of the generated result. This is supposed to improve the precision of the entire program, but now the question is, how do you place this boundary? How do you figure out where to put this boundary for a given ML algorithm? This is where our second insight comes into picture. ML algorithms mostly care about classification accuracy. And then once you have a set of boundary placement that you want to explore, you can you can explore all of them and then choose the one that provides the best classification accuracy. To explain this further, consider an ML inference algorithm given to the framework. The compiler generates multiple fixed point programs with different boundary placements present in them. Now, the number of generated programs is a constant and doesn't depend on the input algorithm. Each of these programs are then evaluated on the training data set, and then their classification accuracies are recorded. The program with the best classification accuracy is chosen and then reported back to the user. So this is the approach that we use to improve precision of the generated fixed point code, and as I'll show in the experiments, this works really well. To explain as part of experiments, we have done experiments on 3 devices, 2 Arduino microcontrollers and 1 Xilinx FPGA. We have tested on 3 ML models, Bonsai, Proton, and a Linnet convolution neural network. We trained our models on a variety of datasets like Cypher, Ladder, MNIST, USPS, and so on. For brevity, I will only present average results across all models and all datasets. For more details about each individual datasets, please refer to the paper. To present our experimental results, I again use a graph with classification accuracy along the x-axis. The rightmost point refers to the classification accuracy of a floating point model, and the leftmost refers to the classification accuracy of a random classifier. On the y-axis is the speed up when compared to the floating point software emulation. The first comparison is with SeeDot. With SeeDot, the average accuracy loss is just 0.8% compared to the floating point models. But the speed up that we achieved is 4.8x compared to the software emulation. These results show that SeeDot is a way better replacement for performing software emulation on these IoT devices. The other alternative was to use MATLAB, which uses high-bitwidth fixed-point representations. Even while using high-bitwidth fixed-point representations, MATLAB struggles to generate programs that give high classification accuracies on certain data sets. Because of this, it suffers from a high accuracy loss of 8% compared to the floating point models. Also, since high bitwidth fixed point is not supported on the microcontrollers that we consider, it also suffers from a huge slowdown, which is 10 times slower than the software emulation. Lastly, there was low bitwidth fixed point techniques that that involve a lot of scale down operations and then completely lose precision at the end. And the classifiers generated by using this approach is random, and they suffer from an average accuracy loss of 46% compared to floating point models. And since these techniques use low bitwidth fixed point, their performance is equivalent to that of SeeDot. So these results show that we have achieved what we wanted to do. We have, with SeeDot, we have generated programs that have very high classification accuracy and the same time can perform very well on IoT devices. The SeeDot framework has two more optimizations. One of them is the optimized implementation of the exponentiation algorithm. Our implementation performs only 2 table lookups and then 1 fixed point multiplication to compute the exponentiation function, and this performs like 23 times faster than the math.h implementation. We also have added a FPGA backend which can generate Verilog code for accelerating machine learning algorithms on FPGAs. The FPGA backend uses 2 key optimizations where we have written custom sparse matrix vector multiplication algorithm in Verilog, and the compiler also generates parallelization hints to the synthesis tool to improve performance of the Verilog code. Overall, the SeeDot generated Verilog code now performs 7 times faster than the Verilog code generated by high-level synthesis tools. Now, with the FPGA backend, an ML expert need not have to write Verilog code of ML algorithms. The ML expert can actually just write a high-level SeeDot program, and the framework can automatically generate Verilog code for them. This improves FPGA programmability. To conclude, I want to say that ML on IoT devices has become an emerging domain with a lot of interesting applications coming up, but there are hardly any frameworks in this space. So we dealt with SeeDot as the first framework, which has a language that can be used to express ML algorithms in very few lines of code. And it has it generates device-specific fixed-point code that runs 4.8 times faster on microcontrollers and 7.1 times faster on FPGAs. The SeeDot implementation is online, and I invite you guys to try. Thank you.
Hello, DJ
Hi.
Cordell. So it seems to me like there's a potential for a very serious loss of precision. In some degenerate cases, you can end up with almost no precision, I think, with this translation. Do you have any way of getting any kind of bound or theoretical result on loss of precision during this translation, or any way to avoid some, I guess, really bad cases when you translate from floating points?
So once we have generated code, we can give bound on, we can give an estimate on what inputs that the compiler will work. If the data sets are, if we can say that if the data sets are in this particular range, the compiler will work really well.
Okay, gotcha. Thank you.
Roshan from UT Austin. Good work and good talk. So I was curious about the number of boundaries that you have actually evaluated, and how much time that takes, and moreover whether there is a common something related to all the benchmarks and the architectures. Is there some trends?
So the most
boundaries the best?
In most of our experiments, 16 boundaries always work. The 16 is based on powers, the bit width that we explore, and that's something which always gives us less than 1% accuracy loss. But
what do you mean by 16?
So the compiler can generate multiple bit width programs. So if you want 16-bit, you can generate 16-bit fixed point code. And if you choose that, the compiler will explore 16 boundaries.
So you said it had support for multiple bit width. Or is this still uniform bit width in a given program, or is this going to be mixed precision?
No, this is just single bit width right now. So we are exploring using multiple bit widths.
Yeah, because that motivates a scale issue. Because typically what you do is you allocate more bits to that output if you're going to overflow and get a mixed precision program, right?
Right. So that's what. So we have seen cases where some variables need more precision and sometimes it's not required. So we are exploring that right now.
Okay, last question.
Yeah, just I can have a follow-up. So the precision like that you allocate, you'd expect like in different parts of the network to be different, right? In the beginning or in the end to be like more high precision than usually in the beginning, and you should have like higher precision.
So we currently have the compiler currently takes only one bit width into account and then generates only one bit width programs. So we have not currently completed the work on exploring multiple bit widths for the same program.
And did you try this for regression, or is this only for classification?
So this works on regression also. This works.
Okay.
Yeah.
All right, let's thank the speakers.